Bismillahirrahmanirrahim. We continue our discussion on processes and start our today's lecture from where we have left in the previous lecture. We first developed an understanding with the term process, and we defined it other than job. A process is a user task in execution. This is what we defined for a process. Then we discussed different states that a process normally obtains while it is in the system. We discussed different types of states, and when they are required, we have discussed that in previous discussion. Then we had started discussion on process state transitions. How a process changes its state from one state to another, what functions or what actions are required to change the states. We discussed one state transition in previous lecture, and that was a two-state model, where we discussed when a process changes its state from ready to running and when it comes back from running to ready. We continue our discussion on state transitions and discuss further more state transitions and state transition diagrams. Let's proceed with other process state models. So today, in today's discussion, we will discuss three-state model to show process state transitions. Along with that, we will discuss some more state transitions in today's discussion. So let's proceed with today's topic. In previous discussion, we had seen a two-state model. Here you can see this is the previous two-state model. Here you can see when a process goes from ready to running due to dispatch function, and when it comes back from running to ready due to its CPU timeout. So we have added another state. You can see ready and run are two states of a process. Now we are adding to this two states model another state, which was, if you remember, we discussed the block state, which was an active stating. In block state, a process waits for some event to happen. For example, a running process may request some input from user. So it goes to the block state. Until the user gives it input, the process will not continue its execution. So a running process requires some event to happen. So here you can see from running state, we reach to the block state as the process requires some event to happen, and the event is only known when the process is executing on processor. So the block function of operating system is called, and the process changes its state from running to block state, which is a waiting state. This is an active state, active waiting. Now when the event happens or when user gives input to the blocked process, the process then goes back to the running state. Here you can see it goes back to the running state, to the ready state, sorry. The process from block state goes back to the ready state. It will not go back to the running state from where it has come to the block state. Keep in mind, a running process can be blocked But a block process, when it gets wake up, it has to then wait for its turn in the ready queue, in the RAM, for its turn to be assigned to CPU. It cannot be ultimately assigned to CPU. Keep in mind, other processes which are waiting in RAM, they have to execute first, and this process goes to sit at the tail of the RAM. So when it is its turn, the CPU is then assigned to it, then the process dispatches and goes to the running state. So the function or the event that wakes up or that makes a process to change block state to ready state is the wake up, or wake up function, or a wake up event, normally we call it. So this is a three-state model in which we have added one more state to the existing two-state model, in which now we have added three states that includes ready, from ready to running, from running to blocked, and from blocked to back to ready state. Keep in mind, whenever you draw state transition diagram, you must label these transitions. This shows the activity or the functions of operating system which happens to change this one state from another. So you need to mention or label the transitions properly. Now let's proceed to the next state transition diagram. Now here you can see, after discussing three-state model, we now have a five-state model. You can see this is the three-state model we have already discussed. Here you can see a process from ready state, it goes to running state and back to from running to ready state. And a running process can be blocked for some event, for any IO request, and it can wake up when the event completes to ready state. So this is the three-state model previously that we had already discussed. Now we are adding another state, which is the suspension state. Here you can see suspended ready and suspended block state. Suspension is one state, so we have split it in two separate states, suspended ready or suspended block. Now what is suspension? Suspension means a process is temporarily blocked or temporarily taken out of the system. Now when a process is taken out of the system, that means a running process or an active process is temporarily stopped to work in the system or to be executed on the system. So there are different reasons when a process is suspended. Suspension state is temporary state. So a temporary process can be suspended and it can be resumed back. Now when a process is suspended, there are different reasons for suspension state. It may happen that a process which is in RAM, but for now it is not required to be executed. For example, you have 4 or 5 applications in your RAM, you have opened them. Suddenly you think that you have some important assignment to submit. So whatever tasks you were performing at the moment will get suspended, and you ultimately open your assignment or your exam preparation slides or whatever, your lecture. So that particular user task which you were performing earlier will get suspended, as you have another task which has more priority than this one which you were currently working on. So that process will go to suspension state. You have temporarily stopped that application and started to study for your exam or started to do your homework. That suspended process is temporarily taken out of the system. Taken out of the system means that is taken out of the RAM. So here you can see when a process is in RAM, ready state mainly shows your RAM. So when the process which is in ready state but you temporarily stops it, so it goes to suspension ready state. That means the process is no longer required in RAM, or it has no space currently in RAM. Now this suspended ready is the virtual memory which we had already discussed in class. So your process gets suspended, but since it was suspended within the RAM, so it goes in the ready state but in suspension. So the process is taken out of active RAM to the passive RAM, which is your virtual memory. When that process is required to be executed, so then it comes back to the ready or the RAM or the active RAM again. So you can see you suspend a process, so it goes to the suspended ready state. It goes to the virtual memory, or it comes out of your system. When you think now is the time to execute this process again, so this process then resumes and comes back to the active RAM again. But here again it will have to wait for its turn to be executed on CPU. So it will sit at the tail of the RAM. Now another suspension. Here you can see suspension, as you have understood, a process which has been temporarily stopped to perform its activities. A process can be suspended when it is blocked. So blocking is an active waiting state in which a process is waiting for some event to happen. For example, it is waiting for some user input. So user input is provided through the keyboard or through mouse or whatever the input device you have. Every device, as we had already discussed, you have single instances of different hardware, different devices in your system. You have single keyboard, you have single mouse. So every device maintains a queue in which so many user jobs, user processes are residing to get that particular device. So at the time, more than one user applications may be waiting for the keyboard in order to be given an input. So if more than one applications are waiting in the keyboard, in the queue of the keyboard to be given input, now it is the user who decides which application to be given input first. So if you select an application to be given input, the other processes which are also waiting for the keyboard then goes to suspended block state. So in that particular device, it goes to suspension because we have selected one application for which we want to give input first. The rest of the application who are waiting for the input for the keyboard or for whatever the input device, they are then sent to the suspension state. So here you can see a block process may go to suspension because we do not want to give it input right now. There could be many reasons, as some other important application who requires the input first. So we give that input, assign the keyboard to that particular process first and keep this process in suspension. So a block process can be suspended, and when you think now is the time to give it the input, you then resume it. So it will be resumed again and it will be at the top of the keyboard queue. You give it input and then it will go back to the ready state in order to be executed again the rest of the statements. So block suspended and blocked ready must be now clear to you. Now here you can see a transition between blocked suspended and blocked ready. A process which was suspended block, when you give it input, but still that is not an important job to be placed in RAM or to be placed in ready. So that process, though you have given it input, but it is not important to be executed next, so it goes to suspended ready state when its event gets completed. But still, either you think it is not important to be placed in RAM to be executed next, or operating system thinks it is not as much important as other jobs in ready queue. So that process is then taken from suspended block to suspended ready. It has been given the input, it has been given the event has been completed for it, for which it was blocked, but the operating system or user does not want to give it place in ready queue. So that goes to your passive ready queue, which is your virtual memory, and reside it here. When this process is given importance or a user wants to get this process be executed, so then it comes back to the ready state. Here you can see, then it comes back to the ready state, and from there it can be executed on CPU. So here you can see we have discussed a 5-state model in which 3 states were previous one, the ready, the running, and the active block state, while the suspension state is a new state that we have added in this diagram. Suspension, we have split the suspension state into categories. One is when a process is suspended when it is blocked, and the other is when a process is suspended when it is ready. Now keep in mind, suspension is again a waiting state. Suspension is another waiting state. And we had also said blocking is also a waiting state. But blocking is an active waiting, while suspension is passive waiting. So these 2 states are passive states. Suspended ready and suspended block are 2 passive states, passive waiting states. Keep in mind, block is active waiting while suspension is passive waiting. I hope the 5-state model must be clear to you how suspension works. Suspension is temporarily stopping a process to perform its activities. The next topic that we are going to discuss related to process is the process control block. We now need to see what is PCB. PCB stands for process control block. So let's proceed with the discussion. Process control block is actually a block that has the controlling information related to a process. The information within process control block is generally organized in shape of a list. So that is why it is known as a block. It is in the shape of a block or a list. A process controlling information is stored in this block. So PCB is created for every individual process. Keep in mind, and where it is stored when a process is loaded in RAM. So wherever place it occupies in RAM, its PCB is loaded along with it. Now, for example, this is your RAM. Top location has been occupied by the kernel. The operating system top location has been occupied, while rest of the memory is divided in user processes. So this is, for example, P1. So its PCB will be loaded along with it here. PCB1 will show the controlling information related to process 1. Similarly, other process P2 is loaded here at second place. So its controlling information in PCB will be loaded along with it. So wherever your process resides, its PCB resides along with it. So the process P2 has PCB P2 along with it here. So every process has its own PCB. Every process has different controlling information, so that is stored in their respective PCBs. So keep in mind, every process has its own respective PCB. Since the requirements or the controlling information of every process is different from other process, so that is why it is important to have a block for every process that contains its controlling information. Now, what sort of information are required to be stored in PCB? Everything that a process requires for its execution, that is stored in PCB. So this information basically helps operating system to identify what a process requires next. This is a list of information here. As you can see, these are some of the information which is normally included in or stored in PCB. For example, the process states. We have discussed different states earlier. So the current state of a process is stored in PCB so that operating system can know which process is in running state, which process is waiting in ready queue, which process is in block state. So this is for the identification or for the information of operating system. Next, the program counter. We had also discussed earlier what is a program counter. It is mainly a register that holds the address of next executable statement. So program counter is also stored in the PCB. Then some of the CPU registers. Now CPU register, will be discussing them in coming chapters. Mainly these registers are for the protection of a process. So CPU registers are there that holds the addresses. Keep in mind, registers holds the addresses. Then the CPU scheduling information. For example, how much time a process has been assigned or how much time of CPU has been assigned to a process, that information is stored in this section. Then memory management, anything related to process memory, so that information is stored in PCB. For example, the size of the process, what type of storage it would require. So all related to memory information is stored in PCB. The accounting information, accounting here means anything remaining is stored here. For example, if a process requires 20 milliseconds of CPU to be assigned to it, but initially it is assigned only 10 milliseconds, that means a remaining 10 milliseconds it will have to come again to be executed on CPU. So that remaining, how much time it has executed and how much more time it requires of CPU. So that is the remaining information is stored in the accounting section. And then the IO information, how many times it would require to receive input from the user and how many times it would require to display the output to the user. So IO status information, so anything related to IO will be stored in PCB. So this is a list of some of the information which a process must require to tell operating system what it has to do next. So when a process comes in ready queue, operating system generates its PCB and keeps on looking at the PCB in order to know what a process would require next. Now this is the structure, the list. As we just said, a process is organized, the PCB is organized in shape of a list. So here you can see this is the structure of PCB in RAM, which contains different information related to every individual process. A PCB is created for every individual process. So every process has its own PCB. So the information, what is the information that is required? The state of the process number. Now the process number is actually the unique identification of the process. You normally give some name to your task, which is uniquely identified by you. But operating system gives its unique number. You identify it by the name you give to your application, but internally operating system gives its other unique number, which can be some hexadecimal number, for the identification by operating system. So operating system does not identify an application by your given name. It identifies by its own given unique number. So this is the process unique number. It is similar to the unique key you generally, or the primary key, or the registration number you generally have in the databases or in your classes. Every student has its own respective registration number. No two students can have same registration number. So similarly, every process has its own unique process number. No two processes can have same number. Then the program counter information is stored here. The CPU registers are there. The memory management information there. Other related files, for example, a running process may require support of other files. For example, when you write a program in C, so you need to obtain information, or you need to obtain other functions which are not defined by you. For example, you use cin function. Now cin is a function which has already been developed and stored in the directory. So these are the helpful files. So you give the link of the directory, so for the execution or for the help of your application. So any file which are related or which are to be required by this process, and those files will help in the execution of this process. So all that list will be stored. The names and their location, their addresses will be stored in PCB. So all these and other related information which we just discussed in the previous slide are stored in PCB, and the structure of PCB is in the form of a list. So this is a structure of a single PCB for a single process. For example, the process 1, so its PCB is having structure like this. The next topic that we are going to discuss is within the process is the operations that we generally perform on a process. Now, some of the operations are performed by user on processes, while some of the operations are performed by the operating system. So there are so many operations that can be performed on a processes. Some can be performed by the user, while some can be performed by the operating system. So let's see what are some of those type of operations which can be performed on a process. So here's a list of those operations which either a user can perform or can be performed by the operating system itself. For example, a user can easily create a new process. When you click on new within some application, that means you are actually creating a new process. So you can easily create a new process, a new application, a new task for yourself. Then if you want to terminate a process, so destruction of a process is the second operation. If you remember, when we were discussing states, termination was the state in which we said a process goes to an end. This is the end of the life cycle of a process. So destroy a process means termination. Now termination are of two types, as we discussed. One is the normal termination, and in some cases we need to abort a process. So a user can normally terminate a process, destroy a process normally. For example, a process completes its execution, the results has been given to the user, and the process is no longer required. So you close that application. That means a process has been destroyed normally. But in some cases, when the process is not functioning normally, or it is affecting the performance of other processes, so in that case, a running process can be by force killed either by the user or by the operating system. So destruction can be of two types, can be done either by the user and by the operating system itself. But destroying or termination is an operation which can be performed on a process. Then suspending a process. As we said, suspension is a state in which a running process or an active process has been stopped temporarily. So a process can be suspended either by you, either by the user or by the operating system. If you ignore a process, that means that process needs to be suspended. So operating system on your behalf, on user behalf, suspend that process and puts it in the suspension list. Now when that process is required to be active, so that process from suspension comes to the active state, and that action or that operation is known as resumption. So the process resumes its active state. So active states are the ready states, the running states, and the active waiting block states. So after suspension, it can be resumed either by the user or by the operating system itself. Our operating system normally resumes a process from suspension on behalf of the user. Now changing the priority of a process. This is another operation which is commonly performed on processes. For example, if a process, some of the processes are least important, so that means their priority is low. And some of the processes, some of the user applications, some of the user tasks are more important, so their priorities are generally high. So here we change the priority of a process. This can be done by the operating system on user behalf. The next operation that is performed in a process is blocking a process. Blocking is the state actually in which a running process has been sent to some device for the user to give it some response in shape of, for example, the keyboard entry. So in this state, a process waits for the event. So that event might be from the operating system and that event might be from the user. So the process waits for some event to happen. This is an operation. And when that event happens, a process wakes up again and starts its normal functions. So the waking up of the process is another operation which is being performed on a process, and that is performed by the operating system. Then dispatching. Dispatching is a function in which a process from the ready state has been sent to the running state. So in dispatch, this is performed by the operating system. It sends a process from RAM to CPU. This activity is known as, or this operation is known as a dispatching. Then another operation is to enable a process to communicate with other processes. This operation or this activity is known as inter-process communication, in which operating system allows two processes to communicate with one another. And how this communication takes place, we have a detailed discussion in a separate chapter. Later on, we will see how two processes can communicate with one another. So these are some of the operations which are generally performed on processes. They can be performed by the user and they can be performed by the operating system on behalf of the user. That is all for now. We'll continue our discussion on operations on processes in the coming lecture as well. We'll discuss some of the operations in detail, as some of the operations are quite complicated or quite tricky, which require some more elaboration. So we'll be discussing them in the coming lecture. I hope the topics we have discussed so far about processes are clear to you. If still you have any confusion, any query, you can email me or ask me on KCMS. That is all. I thank you all.